Given w of x comma y equals x squared y plus x times sine of y, and x of t equals t to the seventh, and y of t equals sine of 2t, find dw dt. So what we're going to do is start by drawing a thing called a dependence diagram. Now these diagrams will look different for each problem, and so in this specific example, you'll see that w depends on x, right? So it's w of x comma y. And so we'll draw an arrow from w down to x, but it's x comma y, so w also depends on y. We'll draw an arrow from w to y as well. Looking at the x formula, x only depends on t, right? To the both in the parentheses here, x of t, and then to the right, where the only variable you see is t, x depends on t, so we'll draw an arrow from x down to t, and then y depends on t, we'll draw an arrow from y down to t. So this is going to always depend on the example, on the problem you're looking at. But for this question, this will be our dependence diagram. So you see an arrow pointing downward each time that one variable depends on another variable. And then what we're going to do is use this dependence diagram to write the specific version of the chain rule. And so unlike the chain rule from first semester calculus, this is all a little more involved, but it's not too bad. So what we do is we look at, there's a path from w to t, right? So dw dt, let's look at all the paths from w to t. So there's the path from w to x to t, and so we write down dw dx times dx dt, and there's a path from w to t that goes this way, w to y to t, so we write down dw dy, that's a typo there, sorry, I'll fix that, times dy dt. So what we end up with, plugging the pieces, right, taking some derivatives based on what's up here, the partial derivative of w with respect to x, so 2x plus sine y, and then the derivative of x with respect to t, so 7t to the sixth. Then we need the derivative of w with respect to y. So looking at this, we should have an x squared plus x cosine y. And then we need the derivative of y with respect to t, which itself, the derivative of sine of 2t should be 2 cosine 2t. And then we need to just replace some intermediate variables. So that is, wherever we see a y, we should just replace with sine of 2t, and wherever we see an x, like there and there, we should replace with t to the seventh. So it looks a little longer and messier, but we did, in this last step, replace intermediate variables x and y. This looks a lot like how we had to replace intermediate variables in the review Calc 1 style chain rule problem that we did. Let's do another example. So find the partial derivative of w with respect to s. W is x squared plus 3y cubed plus xz to the fourth. X depends on both s and t, and x is s to the fifth, t to the seventh, and y depends on s and t. Y is sine of s times sine of 2t. And z depends on s alone. It is ln of s. So this is our dependency diagram. I hope that looks okay. Just take a minute to stare at this. Every time there's an arrow downward, it's because, for instance, why is there an arrow from y down to s? It's because if we look at the formula for y, it has both s and t involved. Okay, so based on this dependence diagram, we're going to now, we would find the partial derivative of w with respect to s by looking at all paths that start at w and end at s. So this is what the specific version of the chain rule would look like. The partial derivative of w with respect to s is dw dx times dx ds plus dw dy times dy ds plus dw d, that should be a z, sorry for that typo, fix that, times dz ds. And so we get a thing that looks like this. I won't bother through all of the partial derivative computations, and then we're not done. We just need to replace intermediate variables. That is, every time we see an x, we should now replace with s to the fifth, t to the seventh. Every y should be replaced with sine of s, sine of 2t, and every z should be replaced with ln of s. And in the end, you get a thing that looks like that. Sorry, it just looks kind of messy. It just, the problem grew in how much you need to write. But now we have something that's entirely in terms of s and t. So just as a note, the intermediate variables x, y, and z are replaced in the last step. And we happen to write dz ds instead of curly dz over curly ds because s does not depend on multiple variables. So right? So because does not depend on multiple variables, z up here only depends on one variable. So it's a calc1 style function. And so we use this curly d shape when we're really talking about partial derivative. In the case of differentiating z, there's only one input variable, so it's not a partial derivative. It's like a standard calc1 derivative. So let's look at the partial derivative of w with respect to t. It's all the same setup as before, all the same w, x, y, z functions. It's just we're looking at partial w with respect to t. If I go back to the previous slide, it was partial w with respect to s. So same dependence diagram, but we now have dw dt equals dw dx times dx dt plus dw dy times dy dt. And so we compute those partial derivatives and then, of course, replace the intermediate variables. Okay, again, intermediate variables were replaced. Interactive question. How many terms should there be for the partial derivative of w with respect to s? I think this is basically given away here, but I want you to really just think about why there's a certain number of terms for dw ds versus dw dt.